Current AI engineering focuses on scaling memory through million-token context windows, retrieval-augmented generation, and agentic task decomposition. These advancements allow systems to execute impressive short-term actions, but they struggle to maintain coherence over weeks of continuous operation. Long-horizon reasoning requires maintaining operational coherence and governing rules across time, interruptions, and revisions. This structural requirement remains constant regardless of the total number of steps performed. This data stream represents a process over time. As it grows, information on the left fades to gray. The system loses the continuity needed to treat early instructions as binding. Fractures appear in the sequence. Text remains accessible, but early conditions lose their operational force. Context windows serve as storage for language. They do not possess the mechanism to preserve structural constraints over an extended horizon. A standard AI transcript is a record of what was said, but it fails to distinguish which parts of that history remain authoritative. In an operational environment, a system must know what is currently binding, not just what was previously generated. Summarization techniques strip away the exact conditions that made a claim valid. By compressing details to save space, the system removes the context needed to enforce its own rules. This results in assumption laundering. A tentative, unverified claim from early in the process is repeated until the system treats it as an absolute factual premise, ignoring its original uncertainty. Simultaneously, systems suffer from constraint evaporation. Hard rules mentioned in the initial prompt lose their force as the active context fills with new subtasks, eventually becoming inactive noise. Retrieving a memory of a rule is functionally useless if the system's architecture lacks the capacity to let that rule restrict its current behavior. We can observe these failures in a multi-month engineering project, an AI agent framework tasked with designing a regulated financial platform. Month 1 establishes a hard invariant. Data must remain in a specific jurisdiction. Months 2 and 3 stack new features on top of this requirement. But in month 4, an optimization reroutes data, severing the structural relationship with the original jurisdictional rule. The system allowed this because the performance agent's code passed its immediate efficiency tests. The month 1 rule was buried in the logs, no longer exerting influence over the current task. This is dependency drift. Upstream components change, but downstream actions continue as if the original premises were still valid. Multi-agent systems are vulnerable to this because local success and test passage do not guarantee global validity once the overarching structure is lost. Wesley Shu's energetic paradigm addresses this by treating long-horizon reasoning as the governance of an evolving state machine rather than the generation of text. This is the EP state formulation equation. These variables form a geometric lattice, serving as the system's structural core. The invariants act as the rigid outer boundary. Inside, dependencies function as load-bearing struts, tracing the lineage of every decision. The BT and UT variables track internal capacities, treating compute budgets, risk tolerance, and agent permissions as finite, shrinking resources. In this paradigm, energy is a technical measure of operational resistance. This energy represents the restricting force a past decision exacts on the future available actions of the system. A legal prohibition carries high energy because it removes specific pathways from the set of admissible future states. By converting passive memories into active geometric constraints, the energetic paradigm ensures the past continues to shape the feasible future. System progression in EP occurs only through admissible transitions. Every move from state T to state T+1 must satisfy the rules of the structural state. Returning to the financial platform case study, we can see how EP handles the rogue month 4 performance optimization. When the agent proposes the global data path, a verification pulse shoots backward through the lattice, testing the transition against the dependency lineage. The pulse strikes the month 1 jurisdictional boundary, it flashes red, and the proposed transition is repelled and quarantined. This structural quarantine enables safe pause, resume, and revision. Because the dependencies are mapped, the system identifies exactly which region requires repair without restarting the entire project. Every step is evaluated against the entire horizon. Progression is authorized only if the governing conditions of the project remain intact. Standard systems are prone to the completion illusion, where finishing a planned sequence of steps is mistaken for achieving the objective. In the energetic paradigm, task success is measured by the integrity of the structural state at the final step. This architecture allows for safe branching, delegation, and even the swapping of underlying models mid-project. The transfer package is a binding structural state that preserves all constraints and obligations. As shown in this comparison, the 1D text line on the left crumbles as it grows. The 3D lattice on the right demonstrates that constraints can remain active and governing even as the transcript is compressed or the task expands. Long-horizon intelligence is the capacity to remain structurally coherent while navigating continuous change. It is maintaining binding constraints throughout the life of a task.